see those lectures, you can see those. Page 3 is important because if you see along with the lecture schedule, there is a class test schedule given for us. Okay, so the first class test will be on 6 September during the class hours. Okay, so 6 September I think is a Monday. So Monday we will have the class test. Okay, so Monday we'll have class test all the 3 Mondays. That is what we have. Okay, so these 3 dates are important. But tentatively, these are the dates for your examinations. And Monday, okay, Monday during the class hour, we will have tests. So that is something that you have to remember. And this, okay, page 4 only class details. Okay, so nothing much for us to worry. So whenever Somesh Kumar sends email saying announcement about section 2. You have to remember that you are in section 2, right? Don't confuse with your first year section. Okay, let me start. Okay, somebody has already started the recording. Okay, thank you. So so this is about the course syllabus and exam dates, which is most important thing. And let us continue our discussion yesterday. Okay, so we started with random experiment, sample space, different types of sample spaces, and what we mean by events we understood. And now the important task now, once you identify what the events are, is actually the probability assignment. Okay, so we want to assign probability to the events. And what we were looking at, this particular example. What was the example? The example was tossing a coin. And suppose a coin is given to you and you want to assign the probability of heads, and you don't know whether the coin is unbiased or not, right? So the problem is you are unknown about the unbiasedness of the coin. If you know the coin is unbiased, then you know that probability coin is unbiased. Same thing as saying both the outcomes are equally likely, right? Heads and tails are equally likely, so the probability is half for appearance of head. But the problem is we don't know whether the coin is unbiased or not, and now you want to do the probability assignment. How would you do this probability assignment? So the suggestion was repeat this random experiment n number of times. What is the random experiment? The random experiment is of tossing the coin. So you toss the coin n number of times. That's what you do. And if you toss the coin n number of times, you find out the relative frequency. We are calling it FA. So what is the relative frequency? Relative frequency is total number of heads you will count in the n tosses, right? So this is the ratio, relative frequency. Obviously, this ratio is between 0 and 1, right? So these are the properties. So let us continue our discussion from here. Okay, so let's quickly revise. So what we did, repeat the experiment, random experiment R n times. Okay, so n repetitions are done. And then we define this number f of a to be equal to number of heads, total number of heads in n tosses divided by n, right? Which is called as relative frequency. Okay, relative frequency. This is the definition of relative frequency. And then the idea was you let this n to go to infinity. Okay, let this n to go to infinity and see if this number fa converges to some number. Okay, let us call it ea. Okay, let us see whether this happens or not. If this really happens, the guess was, the suspicion, the intuition was that as you increase n, this is what is going to happen. See if this fa tends to pa or not. And if this fa tends to pa, some number, if this fa converges to some number, let us call it pa, and say that this is, so assign this number, okay, assign this number pa as probability of a, or probability of observing head. So there are a lot of things happening here. Okay, so the first thing is that whether this thing will happen or not. Okay, so whether this thing is going to happen or not. That is the first question. Okay. So other question, other observation is the following. Okay. So R repeated n times and calculate FA. Okay. This bracketed part, what do? I repeat n times. I can do that. Do you all agree that I can do that? I have a coin, I'll toss it 10 times, I'll calculate relative frequency. Then I'll toss the coin again n number of times and I'll again calculate the relative frequency. What do you think? Are the relative frequencies going to be the same in both the cases?
No, sir.
No, the relative frequencies might differ. And in fact, if you do m such repetitions of these runs, then what will you have? You will have m different candidates FA. Is that right? Do you understand what I'm saying?
Yes, sir.
Yeah. So you will have m different candidates. So there is a variation between the values of these FAs, right? There is a variation between these values of FAs. So for example, these values might be something like this. So suppose you take n is equal to 10. Okay, I'll take n is equal to 10. Then in the first case, I get FA1 is equal to 9 by 10. That means that I observed 9/10 out of 10. In the second time, I observe FA2 to be equal to 3 by 10. That means that I observe 3/10 out of the 10 tosses. And I have FA3, I have 1 by 10. Okay, I observe only one head in 10 tosses. These are all feasible values of FA. No problem about these values of FA. Do you all agree? That's perfectly fine.
Yes.
But now you see what is really happening. If you do m is equal to 3, then you have these three values of FA. You see the value, the change in value of FA. It is going from 1 by 10 to 9 by 10, right? That is the range of FA that you can see in these m observations, right? So there is a lot of variation in these FA values. So other interesting thing that we would like to note is that if such a thing happens, that if FA really converges to a real number PA, then this variation will also decrease as n tends to infinity. The variation in values of FAs that you see here, that will also decrease as n tends to infinity. Do you see that point? So had I done more tosses, like I had done 100 tosses, and if the coin were fair coin, that means that you know that the probability is really half. Then do you think the values will be closer to half than they are when you have n is equal to 10? Do you intuitively believe that?
Yes, sir.
In fact, that was your intuition, right? That was your idea to start with this experiment, right? You let that n to go to infinity. So hypothetically, what is going to happen? You are going to let that n to go to infinity. And when that n goes to infinity, wherever this value fa converges to, that value, that real number PA, you will call the probability, and that's the probability that will assign to this particular event A, which is nothing but observing head when you toss a ball. You understand this experiment? Is there any doubt about this experiment? Any comments on this? Please speak up right now. This is very important concept, okay?
So,
Yes.
so why are we repeating this tossing of n times to m times? I mean, we can just straight away toss mn times, right? And
Yes,
then we can get only
yes,
one
yes.
value.
You could have gotten that, but what I really wanted to show, see, in real life situations, so these are all the things that are going to come back to us. So in real life, what is going to happen is that you are only going to get a sample of size n. You will not have liberty of having m different samples of size n. Okay, that is what happens in real life. But now, because we are doing simulation, we want to understand some theoretical properties, like how much is the variability in the value of FA that you calculate at this particular stage. We want to study these things. Okay, so that's why I said you repeat this experiment n times. But you are right, in real life scenario, you will not have this liberty. In real life, you will have only one observation set of size n. Or in this particular case, if you can do this m repetitions, then you will better do size mn sample. Okay, so this is good observation, but this is for our own sake, theoretical understanding. Okay, that's why I'm saying this.
Okay, sir.
Yeah. Any other observation? So
Sir,
do you
could you
have?
please
Yeah. Sorry. Go
could
on.
you please repeat for the n tends to infinity once more regarding the
Yeah.
n tends to infinity?
Yeah. So n tends to infinity. So what is going to happen? When n goes to infinity, what is going to happen? N goes to infinity, that means that you are doing more and more and more tosses. So you did 10 tosses and you observe how many number of heads you got. So if you got 3 heads out of 10, 3 by 10 is your value of it. Now you take that n to 100. That means that you toss the coin 100 number of times. And out of this 100 number of times, you observed how many number of times you get heads. You counted that. Suppose that number is 64. So you have value of FA to be 64 by 100. Okay. Now, suppose the coin that you started with was a fair coin. We don't know that, but suppose that coin was fair coin. I am telling you that information. Then as you increase the number of tosses, what do you expect to see in the value of FA? That's the question we are asking. Okay. So if the coin is unbiased, that means that if the probability of obtaining heads is half, okay, suppose if that is the probability, then do you think that the value FA will converge to half as n tends to infinity? As you do more and more coin tossing, you toss the coin 10,000 number of times and you observe the number of heads that you will have. Do you think that the heads will be close to 5,000, near 5,000, so that the value FA will be close to 0.5? Does that follow? Like, I'm not giving you the proof, but I'm asking, do you have this intuition? That's all. Nikhil?
Yes.
Okay. So that's what you have to observe, or that's what you have to feel. I'm not giving a mathematical proof, but I will prove this in our course itself. Okay, when I have enough tools developed in this particular course, why this FA converges to PA, why this variation in values of FA decrease as you increase the N. Okay, all these things I will prove in this course. Okay, we are going to prove mathematically with like theorem proof statement why this thing is really going to happen. But I just want you to have the feel for this thing right now. Do you have this intuition? Like, even if the coin is not fair now, if it is biased coin and probability of obtaining heads is 3 by 4, for example, 75% probability of having head, then you toss the coins. As you increase the number of tosses, the number of heads that you will count will be close to 75%. Do you have this intuition? Is that okay?
Yeah, right now it's okay.
Yeah, so that's all I'm saying. That's all I'm saying. And if you still fail to have this intuition, all of you can do a very simple exercise. Okay, you can learn Python now. You all of you are obviously going to learn Python. So start your first Python exercise today. What you do is you write a very simple Python code, and in that Python code you simulate the scenario of tossing a coin, or you simulate the scenario of throwing a fair die or unfair die, whatever. You assign probabilities and you pretend that you do not know the probabilities. Okay, then what will you do? Then you will toss the coin or you will throw the die. That is the simulation that you will do. You take n is equal to 10, you take n is equal to 50, you take n is equal to 100, 500, 1000, 1 lakh, 10 lakh, 1 crore. You take all these values and you see what happens to these FA values. Do they go to the probabilities with which you started your simulation? You check that. Do you understand what we can do?
Yes, sir.
Yes,
So
sir.
this same experiment, like tossing a coin, you cannot keep on tossing a coin 1,000 times, right? Computer can do that for you very easily. Ask Python to do it for you, right? So Python, write a simple Python code of 2 lines, 3 lines, and then you see if these things are really happening. You check for the variation between the values of FA. So you repeat this experiment of tossing coin 10 times, 30 times, 40 times. You see the variation in these values, and you see how this variation actually reduces. Okay, so that is something that is very interesting. You can actually see, you can actually observe in front of your eyes. So what I'm saying will be actually done in front of your eyes. But now you understand one thing. What is important thing, that assigning probabilities probably is not as easy as it seemed when you started this course, right? Coin diya hai, probability half. Die दिया है, probability 1/6. Right? We start from there. We don't even think whether they are equiprobable or not. But in real life situation, when you are an experimenter and you want to model that real life phenomena, please try to appreciate this now, that it might not be as easy as it seems to assign probabilities. Right? You have to do a lot of work. You have to do a lot of digging, a lot of work, and you should have a lot of intuition when this exercise comes of assigning probabilities. So is this part clear to all of you? So far,
Yes.
so good. Yeah. So this is something that you have to observe. Okay. Now that we are talking of this thing, once I assign probability of heads, what happens to probability of tails? Do I need to do the same exercise for probability of tails?
No,
So
sir.
this is
No,
complement.
sir.
Why? Why?
It's only 2 out of 3 just.
Okay, so if I have probability of heads is equal to 3/4. For example, I have a biased coin, and the probability is 3/4. Then what will happen? What will happen for probability of tails? Do I need to do this exercise again? I can do this exercise again, but you are not willing to do it. Why? What will you assign probability of tails equal to?
Complement
1
of
minus
that.
probability
1/4.
1/4. So once certain key probabilities are assigned, all other probabilities are getting automatically fixed. So you have certain feeling, or you have certain inclination or certain intuition about the laws of probabilities already, right? So you already have this feeling that this should happen, right? So the total probability should be 1. All these things you already have as your intuitions, right? So this probability assignment. So for example, take another example of throwing a die. Suppose I throw a die. If I assign probability of observing 1, are all other probabilities fixed automatically?
No, sir.
No, sir.
No, the
No, sir.
probabilities are not fixed. If I assign probability to 1 and 2, are other probabilities fixed? No. But if I do it for 1, 2, 3, 4, 5, then are all other probabilities automatically fixed?
Yes.
Yes,
Yes,
sir.
sir.
Yes,
Yes.
excellent. So these probabilities are automatically fixed, right? So this automatical assignment of probabilities is happening because of certain framework, certain rules, certain laws. Okay. So what we are going to do now, is we are going to formally state those laws. Okay, we are going to formally state those laws. So what we are going to do, we have seen this. So the singleton events are there, and then the singleton events, you take union, then that also becomes an event. You take intersections of these things, and then that also becomes an event. So first thing that we are going to do is we are going to define something which is called as sigma algebra. So what is sigma algebra? Sigma algebra is something which is kind of collection of all possible events to which you can assign probability to for a random experiment. Okay, so you start with a random experiment, you form a collection of all the events to which you can assign probability to, and then we define what probability really is. Okay, and then how you will do probability assignment using those rules. Okay, so that is something that we really want to do. So the reason for doing something like this is, first, all your intuitions are now formalized. You have an axiomatic definition of probability. And when you have an axiomatic definition of probability, different people may have different intuitions. They will work with different intuitions. What we will do is we will take minimal assumptions, minimal axioms in the definition. And with those minimal axioms, you will be able to derive many things out of it. Okay, so that's what we are really going to do. So what we want to do, we want to formalize these intuitions we have in the definition of axiomatic definition of probability. Okay, so that is our first task. Okay, so that is what we want to do. And this relative frequency analysis that we have seen here, I just have given intuition. Please remember, I have not given proof for the convergence, but I am saying, I am promising that I will prove this particular thing at a later date in the course. Okay, so this is something that is important, and this is for your own thought process until I really prove this in the class. Okay, so we will do this. Okay, this is very important, and we will prove this later in this course. Okay, so now let us write down these things. Let us see what we can say about these things. Okay, so observation. Okay, so what is the observation that we have made? the observation is that only for certain key events, one needs to assign probabilities. Okay, one needs probabilities. Okay, so for instance, I'll just write you one example. If the random experiment is rolling a die, okay, a random experiment is rolling a die, then we need to assign, we only assign probability of 1, probability of 2, probability of 3, probability of 4, and probability of 5, right? We only assign these 5 probabilities. Then the probabilities of all other events, okay, then the probabilities of all other events are automatically assigned, right? So the key question is, how does this automatic assignment happen, right? How does this automatic assignment happens? Correct? How does this happen?
Sir,
Yes?
sir, can you please reshare the screen because I'm not able to see the screen.
Oh, is it a problem with everybody?
No, sir, it's visible.
No, sir, it's fine.
No, sir, it's
Oh.
visible.
Because I also am able to see this.
Yes, sir. If you're writing on the tab, people have joined after you have shared the.
Oh, so you need to log out and log in again, or what? I think you should use the app. That's what
I don't know about the app, sir, but if you reshare the screen again, it will be visible.
So I have to do it from my side? Okay, I can do it, no problem. So, stop presenting. Oh, sorry. Okay, so I guess now it's visible.
Yes, sir. Yes, sir.
Okay. So how does this automatic assignment happen? Because we intuitively assume certain laws of probability, right? So why it happens? Because we intuitively assume certain laws of probability, right? So what we will do, we will formalize these laws into actions. So we want to formalize these laws into axiomatic definition of probability. Okay. That's what we want. You'll ask, why do you need this axiomatic definition of probability? You have good intuitions, you work with those intuitions, and that's it. But the reason is that once you have this formal definition, you can apply to any experiment that you have. You can apply to any type of sample space that you have, and you still will be able to do all this analysis that you want to do. Okay, so that's the idea. That's the idea of formalism. Okay, so that's why we want to do it. So just to recall, R is the random experiment we are talking about. Okay, so for first couple of lectures, maybe first couple of weeks, I'll write this, remind you with these notations. Later on, I will not do this. Okay. R is random experiment. Omega is the sample space. Okay. Then what is the definition of event? Did we formally write down? Maybe let us write down. Okay, event, a subset of omega. Okay, a subset of omega is event. That is the formal definition anyway. So what we expect? Okay, so we expect union and intersection of events is also an event to which probability will be assigned. Okay. So at this point, I should tell you that all the examples that we have covered so far in this course are such that it was like guaranteed, it was automatic. Okay, it was straightforward. You don't even have to explicitly say this expectation that union and intersection of events is also an event to which probability will be assigned, right? It was so obvious to you. But as you go further, and especially you start looking at the experiment where the outcomes are continuum or uncountable sets, there this problem starts to happen. Okay, so this is something that is beyond the scope of this course, but I'll just give you background in 2 minutes. So what happens? Every event that you think of, every subset that you think of, you cannot assign probability to. Okay. Almost all practical purpose events that you can think of, you can assign probability. But there are certain subsets to which you cannot assign probability to. In our case, so far, such a situation has not arisen. But such a situation arises when you go in the case of random experiments where the sample space is continuum, like closed interval 0, 1. Okay. There will be some subsets to which you cannot assign probability to. And that's why what we want to collect all possible events to which you can assign probability to. And what should happen to that collection? That collection should be closed under union and intersection. Why? Because you also expect that if you assign probabilities to certain events, their union and their intersection, you should be able to assign probabilities. Okay, so that is your expectation. So that is first observation, and that observation gets translated into the definition of sigma algebra. Okay, so the first definition that we want to write down is the definition of sigma algebra, which kind of is the precursor to this expectation. Okay, that union and intersection of events should be also an event to which we can assign probability. So this is little difficult. Yeah, go on. Yeah.
So why do we are taking only union and intersection? I mean, we can also take something like difference and other things like.
So you can always express. So if I have union, intersection, and complement, okay, that is another operation that I have not written in that expect, but another operation is complement. So once you have union, intersection, once you have union and complement, then all other operations are straightforward, right? You can write those operations from these two operations. So that's why I just said. So maybe union and intersection, I should write complement also. Complement of event also is an event. Okay. Complement of an event is also should have the same property, right? So once you have these, then all other things are straightforward, right? So that is first thing that we will formalize in this definition of sigma algebra. So let us write this definition down. So a collection of sets, F is called, okay, so this this F that I have written is like called as calligraphic letter. Okay, so mathematicians always have this fancy about writing different letters. Like I am using Roman letters, which is our normal English script. Then I am using Greek letters like omega, sigma algebra. That sigma I have written down. So this is sigma. Okay, this is small case Greek letter sigma. The capital case Greek letter sigma, I think you already know, it is written as this summation sign, right? Sigma. So this is something that you already have used. So this is capital letter sigma in Greek. This is capital letter sigma in Greek, and this is small letter sigma in Greek. Okay, so this is a Greek symbol, and this is like calligraphic symbol F. Okay, so because it is a set of sets, I am just using a different notation than capital letter. So you will see mathematicians love to have different symbols, right? So a collection of sets F is called sigma algebra. Okay, so I can erase this maybe. Sigma algebra if the following conditions are satisfied. What is the first condition? If A belongs to F, that means A complement also belong to F. So like you rightly pointed out, why should we not talk of complement? So the first rule actually states that we should have complement covered. And if you have these A1, A2, so on, countable collection of sets sitting inside this set F, then what do we want? We want union of I from 1 to infinity, that should belong to F, and intersection of I going from 1 to infinity, that should also belong to F. Okay, so that also should belong to this collection. So F is a collection of sets. Okay, it's a collection of sets. And what are two properties of this collections of sets? The collection of sets should have two properties. It should be closed under complementation and closed under countable union and intersection. Okay, so what are these two laws called as? Closed under. So the set F, so F is closed under complementation, so that is the operation, and countable union and intersection. Okay, so under these two operations the set should be closed. So I hope you are familiar with this terminology, closed under, right? In your second semester math course, you would have studied vector spaces. Then you would have said that a vector space is always closed under vector addition and scalar multiplication. You use this terminology in that course, right? So I'm using the similar terminology. This is a terminology that mathematicians use. So the set is closed under complementation and countable union and intersection. Okay, so that is what this collection should be. Okay, so let us take a couple of examples. The examples are really very easy. Once you see the examples, you'll start seeing how these things are working. Okay, so the experiment is tossing a coin. The first experiment that we were talking of. Okay, sample space is heads and tails, right? So that is my sample space. I take power set. Okay, I take this collection to be power set. Okay, this is what I take. Then is F a sigma algebra? Script F, is it a sigma algebra?
Yes.
So how
Yes,
do you
sir.
check it? How do you check it?
Both conditions are being satisfied.
Both the conditions are satisfied, right? So because both the conditions are satisfied, this is a sigma algebra. Another example, the random experiment is rolling a die.
So why do we call this algebra?
Huh?
Why do we call this algebra?
Okay, why do we call this algebra? Okay, so actually it is also called as field, sigma field. Uh, Actually, it's a terminology. I really do not know why it is called algebra, but it's a terminology. I will just check it up and I'll let you know. Okay, is that okay?
Yes, sir.
Yeah, I will look it up and I'll let you know. There is some reason. The reason lies in a subject which is called as major theory. Okay, so I have not revised that subject for a long time now. So let me just go through it, and if I find out, I'll let you know why it is called algebra. Okay.
So like, can we say the power set of any set is a sigma algebra?
Yeah, you can say that, but the trouble starts at the next level. Okay, so that's why in assigning probabilities the trouble starts. Okay, so for continuous interval 0, 1, you can take f to be that set, and then you start in trouble. So you are looking at all the possible subsets of closed interval 0, 1, and there exist certain sets of closed interval 0, 1 to which you cannot assign probability measure to. Okay, that's the problem. So that's why.
Excuse me, sir.
Huh?
Sir, could you please explain how first example will satisfy those two conditions?
So what is the first condition? You consider any set A. Consider any set A in the collection. Its complement should be there. Is that condition satisfied? What is complement of phi in omega? It's
H,
omega.
comma T.
H comma T. So is that set belonging to the collection?
Yes, sir.
What is the complement of H?
T.
That belongs to the collection. What is complement of T?
H.
H. That is there. What is complement of HT? Empty set. That's there. So the
Right.
first condition is satisfied.
Yes.
What is the second condition? You take any countable collection of unions or intersections. So in first place, you will not have a countable connection here. Even if you have countable collection, what is the union of those sets? So you take any sets from F and take their union. What will happen? Will it belong to F? You take phi and H. What is the union of phi and H?
Sir?
You take phi and H. What is the union of phi and H?
H.
Does it belong to F?
Yes, sir.
You do
Yes.
this for all possible choices of A1, A2, A3. I can take A1 is equal to A2 is equal to A3 is equal to so on and so forth. All these I can take to be equal to the set H. Then what happens to their countable union? It is still H. It belongs to this. I can do anything I want and I still am in that collection F. Is that
Yes,
okay?
sir. Understood.
So
Yes.
that's why this collection F is a sigma algebra. Okay, it satisfies both the conditions. That's why it's a sigma algebra. 1, 2, 3, 4, 5, 6, right? So again, I will take F to be 2 power omega, the power set. Now I'll not list all of them because how many elements are there in the power set?
64.
64.
power n.
2 power 6. Yeah, I think 2 power 6 is easy. Is it 64? 2
Yes,
power
sir.
6, right? So it's 64. That's right. So I'll not enumerate all of them, but that collection is this. So now clearly, like what you saw in the previous example, this F will be a sigma algebra. So all the random experiments, okay, the random experiment R is such that finite outcomes, okay, random experiment with finite outcomes. With finite outcomes, okay. What is omega? Finite set. Okay, so I'll call that 1, 2, 3, 4 up to S number of finite outcomes. Then I take F to be power set of omega. So the number of elements in F, oh sorry, I made a mistake. Okay, I should have written F. Number of elements in F is 2 to the power S, right? So this particular collection F is a sigma algebra, right? So F is a sigma algebra because it will satisfy. So the case of finite outcomes is like kind of sorted. Okay, there is no problem with the case of finite outcomes. Okay. One example which is not very easy, but I'll just state, is that R is a random experiment with 0, 1, closed interval 0, 1 as outcomes. Okay. So what I'm saying really, I have a random experiment whose this omega is 0, 1. Okay. And now instead of taking power set, what do I take? I take all the intervals. Okay. I take all the intervals of omega. So all the intervals in omega rather of the type open A, close B for AB belonging to 0, 1. Okay, I take all these intervals. And then the next thing is that I generate a sigma algebra with these intervals. Okay, so what do I mean? These sets are there, so their complement should be there. Their countable union and countable intersection should be there. So I will take all possible sets of the type AB, open A, close B. I'll take their complements. I'll take countable unions of these sets and countable intersections of these sets, and then I will see what all sets I get. Okay. So all those sets I will put together in F, and I'll generate something which is called as sigma algebra. So this sigma algebra is called as Borel sigma algebra. Okay, Borel sigma algebra. So this is something that is beginning of a very advanced mathematical course called as major theory. And the reason to take this Borel sigma algebra to define probability and not the power set is very involved. Okay, so you need to do a lot of work to see why you cannot take power set, but you have to take this Borel sigma algebra. But for us, you see all the intervals are covered between 0 to 1. Do you see that? All the intervals are covered. Will the singleton sets be part of this this set omega? Will the singleton set be part of this omega? So, sorry, F, the script F. So, will this script F, the sigma algebra, will this contain singleton 0 as an element? Will this happen?
No, sir.
Why not?
Sir, because it is open at A always.
If it is open at A, then what can I do? Can I take complement? So I take, so 0, so see what is happening. So half and 1. Does this belong to, is this the interval of the given type?
Yes.
So its complement
sir.
also should belong. Its complement should also belong. So what is the complement of this set? So suppose I take this as A1, then what is complement of A1 is 0 half. Is that correct?
Sir, shouldn't it be closed at half?
Sir, we close the
Yes.
again.
It will close it now.
It will
The
be
right
closed.
side.
Okay, you can have it closed at half. Now what I'm going to do, you tell me. How can I show now that singleton 0 is an element of F? Can I show it?
Take 0 to 1.
Yes,
Huh?
sir. We can take A1 is equals to 0 to 1. 0.
Take 0 to 1. If I take 0 to 1, then what is the complement? Complement is empty set, right?
No, sir. 0 is.
Oh, sir, singleton 0. It does not include 0, right?
Yeah, correct. So you take 0 to 1. That's what you take. Then the complement will be singleton. So the singletons are there. Once the singletons are there, all the countable sets inside 0 to 1 are there. All the intervals are there. All the sets that you can think of. Excuse me. All the sets that you can think of. Those sets are there inside this sigma algebra that you have generated. Can you see that now? So many sets to which you want to assign probability to. So the practically all the sets to which you want to assign probability to are covered in this Borel sigma algebra. Is that okay? Think of this. This is not easy. You will not understand this in first shot, but try to think of all these different scenarios and all the sets that you might be interested in assigning probability to. They probably get covered by this Borel sigma algebra. So you don't want to go to this power set always. Okay, this Borel sigma algebra is a set which is not the power set. So there are certain sets that we are skipping, which are subsets of omega power set, but they are not part of this Borel sigma algebra. So we'll not go into those details, but this is sufficient for us. Okay, so this is one example of sigma algebra. In the case
Excuse
when,
me, sir.
yes.
So we can say that when discrete values are present, we use sigma algebra, and when continuous values are present, we use Borel sigma algebra.
So Borel sigma algebra is a particular name given to the sigma algebra. Okay, so yeah, you can say that. That's fine. For you, this much understanding is enough. No, that's okay. Okay, and now once we have understood what are all events to which we want to assign probability to, we actually define what is probability. Okay, so let us define what is probability axiomatically. Okay, so let us write down the definition. So what is the definition? Let omega be the sample space for a random experiment. Okay, let F be the sigma algebra associated with omega. Okay, so you have found the sigma algebra. You have started with the sigma algebra. Then a probability measure. So the probability is a measure. Okay, so we'll not get into this details, but probability measure. So if you want to skip this word measure, you can skip it. Okay, it is not really very important. So probability P, I'll denote it by P, is a function. So what is it? It's a function on F to R. Okay, so basically probability is a function on F to R. Okay, and what does this do? Which satisfies such that, so this function has to satisfy certain properties. What are the properties? The first property is that probability of A should be greater than or equal to 0 for every A belonging to. The probability should be non-negative, right? Of any event. That is your intuition that gets formalized into the first action. The probability of sample space is equal to 1. That means that you have enlisted all possible outcomes in omega. There is nothing more possible outcome for the random experiment, right? That's the second thing. And the third thing is about automatic assignment, right? So what is that? So if you have key events assigned, then all other events get automatically fixed. How? Through this third law, roughly. So if AI are mutually disjoint, so what is mutually disjoint? Mutually disjoint for I is equal to 1, 2, 3. So it's a countable collection. And what is the meaning of mutually disjoint? AI intersection AJ is equal to an empty set for I not equal to J, and IJ both will go from 1 to 3 up to infinity. Okay. So whenever you take two different sets in the collection A1, A2, their intersection is empty, right? That is mutually disjoint. Then probability of union AI, I from 1 to infinity. So this probability of union becomes summation of the probability. Okay, these are the three axioms. So if a probability measure, if a probability function that you can think of satisfies these three properties on the sigma algebra, then it is called a probability measure, right? So now you go back to the example of tossing a coin. All these conditions are satisfied by the assignment that you made, right? All these conditions are satisfied by the assignment that you made. So your job is done, right? So that is a probability measure. So this becomes really helpful in the case where you cannot actually enumerate or enlist all the events, okay, all the outcomes. This is especially helpful. This type of axiomatic definition is especially helpful in a case like this, okay, in a case where the outcomes are continuum, okay. When the outcomes are finite, the sigma algebra is just power set, okay. You take that sigma algebra to be power set and then your job is done. It's straightforward. But when the outcomes are not finite, then this sigma algebra really is a very important thing, and that comes to be very handy. So is the definition clear? What are the axioms in the definition? Is this part okay?
Yes, sir.
Yes, sir.
Okay, fine. So let us like somebody said, probability of A complement is 1 minus probability of A, right? So that has not come in the axiom. So that intuition you had, but it has not come in the exam. So if it is not come in the exam, then you should be able to prove it based on the exams, right? So there are certain properties. I think those properties you might have seen already. So those properties now based on these exams will be able to prove. Okay. So let us quickly prove these properties. Okay. So let us quickly prove the properties one by one. So the first property is, so now what I am going to do, I am not going to write things again and again. So there is a random experiment, there is a sample space, there is a sigma algebra, there is a probability measure. All these things are there, and A, A1, A2, B, C, so on so forth, they are all events belonging to this F. Excuse me. Okay, they are all events belonging to this sigma algebra F. Okay. So I'm not going to repeat everything in the statement. I'm just going to write down the properties. So probability of A complement is 1 minus probability of A. Okay, so how do you prove that? Everywhere you draw Venn diagrams, life becomes easier. Okay, so this is omega, this event is A, so this is your A complement. So what do you observe? So now everywhere in this you have to observe. What is the observation? Observation is A union A complement is omega, and you note that this A union A complement, this union is a disjoint union. Is that okay? Because A intersection A complement is empty. So this will tell me that probability of A union A complement is probability of omega. This probability of omega is equal to 1 by the second axiom, right? In the initial proofs, I will write this thing down. Okay, so this by second axiom. And now I can write down probability of A union A complement is probability of A plus probability of A complement. And why is that? So this is coming because of axiom 3. Is that correct?
Yes, sir.
Yes. So once you observe that, then the proof is over, right? Then P of A plus P of A complement is equal to P of omega is equal to 1, which means that P of A complement is 1 minus P. Straightforward, right? Many of you must be thinking, why in the first place you want to prove something like this? But these are some simple consequences that you can see how you can use the axioms to prove. Okay, that's why I'm doing this. You may have had the same problem with the axioms in the vector spaces, right? You would have thought, like, who proves that 0 is unique? Who proves that 2 plus 0 is 2? And all those things you would have done, right, with the confusion. So these are the illustrations of certain ideas that we have. They also have some solid mathematical framework, right? So that's it. The second property is probability of empty set is 0. How will you prove probability of empty set is 0?
A probability of sigma equal to 1, and using the first property you can prove this.
Correct, absolutely right. If A is a subset of B, then what happens to the probabilities of A and B? What is the relationship between them?
Then less than equals to or equal.
Less than or equal to probability of B. Why is that true?
You can see in the Venn diagram.
Again, Venn diagram, absolutely. So what will you do? You will do this to be omega. You have this event as A, then you have this event as B. Then what happens? You can write down B as A union A, B intersection A complement. Is that okay?
Yes, sir.
So what is A? A is this part, pink part. And what is A complement intersection B? A complement intersection B is this ring. Correct? So I have written down B as disjoint union of two sets, A and A complement intersection B. Right? So what can I do? I can use axiom 3. So I will use axiom 3. So using axiom 3, I know that probability of B is same as probability of A plus probability of A complement intersection B, right? Now what is axiom 1 telling me? Axiom 1 telling me that probability of any set is always greater than or equal to 0, right? So can I say that this is greater than or equal to PA and hence the proof? Do you all agree? This is fine?
Yes, sir.
Okay. Next, next property. Probability of, you can say, A union B is equal to PA plus PB minus PA intersection B. This is something that you have already seen with the counting principle, right? Number of elements in A union B is NA plus NB minus NA intersection B. Here we are talking it for probabilities, and the reason why we are talking it for probabilities is we have axiomatic definition in place now. Okay, so suppose this is A and this is B. Okay, how do you write this now? So A union B, how will I write down? I will write down A union B as A union B, A intersection B complement, union A complement intersection B, union A intersection B. And this is a disjoint union.
Yeah.
You are able to follow this, right? Everybody in the class? This
Yes, sir.
is
Yes, sir.
Yes.
fine, right? Okay. So probability of A union B will be probability of A intersection B complement. What is A intersection B complement in this figure? A intersection B complement is this green part, right? So this is this green part, A intersection B complement. What is A complement intersection B? A complement intersection B is this part, right? It is this. And A intersection B is this part, right? This is A intersection B. So I have written A union B as disjoint union of 3 sets, and once I have done that, I can use the axiom 3 to write this thing down, right? But now I want this result in terms of probability of A, probability of B, and probability of A intersection B. I want the result to be in that particular form. So again, A intersection B complement is A intersection B complement. So what is A basically? I can write down A to be A intersection B complement union A intersection B, green and blue. And similarly B I can write down as A complement intersection B union A intersection B, pink and blue. And again I will use third law of probability, third axiom. So this will tell me that probability of A is probability of A intersection B complement plus probability of A intersection B. And this will tell me that probability of B is probability of A complement intersection B plus probability of A intersection B. Is that right?
Yes, sir.
And now I
Yes.
will look at these three equations. 1, equation 2, and equation 3. And then from 1, 2, and 3, what will I get? I get probability of A union B is equal to PA minus PA intersection B plus PB minus PA intersection B plus PA intersection B. Correct? That is what I will get, and this proves the result that we wanted to prove. That probability of A union B is PA plus PB minus PA intersection B. Is that okay? Is it clear? Only set theory, right? I'm just using set theory and using set theory. So next, now you know what I'm going to do. So if A1, A2 and A3 are events in F, then what happens? Probability of A1 union A2 union A3 is probability of A1 plus probability of A2 plus probability of A3 minus probability of A1 intersection A2 minus probability of A2 intersection A3 minus probability of A1 intersection A3 plus probability of A1 intersection A2 intersection A3. How will you prove this? How do you prove this?
First making the Venn diagram.
We can treat A2 union A3 as B.
Correct.
We
That
can
is
take
better.
pair of elements.
That is better. So you treat this as B, you treat this as B and this as A in the previous result and use the previous result to prove this. Venn diagram, of course, you can do, but now you should get hang of the thing that once you do this, I'm going to ask you to do A1, A2, A3, AN. So how will you draw Venn diagram for A1, A2, A3, AN? So use this idea. What is the idea? This is the idea. Use this as B, this as A, use A union B, and then prove this. Can you prove it? Can you prove it?
Yes, sir.
Okay.
Yes, sir.
So next result I want is A1 union A2 union so on so forth AN is. You first tell me what is this probability. And what you have to do is you can prove this using induction. Okay, so I'm not going to do this. I'm not even going to write down what is the right hand side of this. So can you tell me what is the right hand side of this?
Will be summation of PAI minus summation of PA intersection AJ plus summation PA intersection AJ intersection AK and so on.
And so on. Correct. So what is the last term?
Last term is plus minus 1 to the power n plus 1 into P of intersection of all the sets.
So how will you prove this using induction? What will be the argument? At least tell orally.
We can assume.
Yes.
Go ahead, Pradeep.
No, you.
Okay, so we will assume it the union to be equal to that for some k which is less than n, and then we will add one more element to it and prove it for
Okay.
k plus 1 and generalize it.
Okay. So this idea is known to everybody, how to use induction also. Very good. So you can use this mathematical induction, and using the induction you can prove that this is really happening. Okay. So very good. So you can do all these things in your free time. Okay. You can take these as homework. One more thing I want to do before we go further. Okay. So let us write it down. Okay. So it's an interesting property. So let us write this down. Okay. So I have A1, A2, AN sequence such that A1 is subset of A2 is subset of A3 and so on and so forth. So this is a sequence of increasing sets. Okay. So I have a sequence of increasing sets, and this increasing sequence actually is such that union of all these AIs, I from 1 to infinity, is equal to some set A. Okay. Then, so of course, what is happening? All these A1 up to AN, so on, so forth, they all belong to this collection F. Okay. They all belong to sigma algebra. Then obviously A belongs to sigma algebra because A is closed under countable unions. So it is closed under sigma algebra. Then what happens? I have this A. Then what is the statement I want to make? I want to make a statement about this probability of A. What will be this probability of A? Can you guess?
Probability of the last element of the sequence.
But the sequence is infinite, right? There is no last element in the sequence. Can you say there is a last natural number? No. So the same thing. The sequence is countably infinite sequence. But your intuition again is right. So how will you write that stuff? Mathematically, what is it?
The limit as n tends to infinity, an means.
Correct. Limit n tends to infinity, probability of an. Absolutely right. That is what this is. So we want to prove this. Okay. So how will we prove this? Again, Venn diagram. Everywhere we will draw only Venn diagrams. Okay. So this is our sample space omega. And then you draw this set. So this is increasing sequence. So the smallest one is A1. Outside this is A2. Then you have A3. Then you have A4 and so on and so forth. And they all are sitting inside this set A, right? They actually combine. So this is your A, the final unit, whose probability you want to find out. And these sets are A1, A2, A3. So I'll just write down A1, A2, A3, A4, and so on and so forth. Okay. So this is a sequence of sets that is going on, and then eventually you will get. Is the Venn diagram clear?
Yes,
What
sir.
I will do, then what I will do is I'll define new sets. Okay. So I again define new sets. So can you guess how I'm going to define new sets? So far what I have done is given any set, I have tried to write it down as a disjoint union of certain sets. And when I'm finished writing down it as disjoint union of certain sets, I use axiom 3. You see all the proofs that we have done today so far, all the proofs that we have done. Every proof involves this one key step of writing down the set, some set as disjoint union of some sets, and use axiom 3. Everywhere you see in all these things I have done that. So here also probably I want to do that. So if I want to do that, how will you do it? So the way I will do it is I'll define B1 to be equal to A1. Then what will be my B2?
A2 intersection A1 complement.
Correct. A2 intersection A1 complement. So what is that? So what I am doing? Is I have this particular set A1. Then what is my B2? My B2 is basically this set, this ring. Then what will be my B3? B3 obviously from the figure it is now clear. This will be the ring that is by this blue. And then what is B4? B4 will be this, right? So that is what I'm going to do. So how am I writing this in set notation? The way I'm writing this in set notation, B3, what is B3? Can you tell now what is B3?
A2 complement intersection A3.
A3 intersection A2 complement, that's right. So on and so forth. So what will be Bn in general? An intersection An minus 1 complement. Is that right? That is my Bn. So I'm looking at all the rings. I'm looking at all the. So now what I know is that summation of not summation, union of AIs, I from 1 to n is same as union of BIs, I from 1 to n. And moreover, this is equal to probably, this is equal to An. Is that right?
Yes, sir.
Now this is clear. Then what is probability of An? Then probability of An is probability of union I from 1 to n, which is equal to probability of union I from 1 to n, right? This is the probability that you have. And now what do you do?
So now we can write the probability of BI in terms of probability of BI minus 1. And then they will cancel.
So this is what you have. Yeah, that also you can do. What you said is right. You can write down like that. But that operation is actually being implicitly done in this summation. Okay, so what you are saying, you cannot really write it down explicitly. So that is implicitly done in this particular operation, right? And now you have to observe only one thing. What is the observation? Observation is that A is actually union I from 1 to infinity is same as union I from 1 to infinity is nothing but limit n tending to infinity union I from 1 to n, right? And once you do that, your job is done. Okay. Yeah. So that proves this very interesting result. So similar result you can prove for decreasing sequences also. So A1 containing A2 containing A3, and then you look at the intersection of all these decreasing sequence, and you can say the same result about decreasing and so on, so forth, right? So these are some interesting consequences and results which you can prove using this using this axiomatic definition. Okay, so let's go to the next concept. So the next concept that I am introducing is something that is very important. It is called as disjoint cover of omega. Okay, so the next concept I am introducing is disjoint cover of omega, the sample space. So what is the disjoint cover? Let B1, B2, Bn be the collection, be a collection. Of course, it is a subset of F. Please see the way I am doing this. So the collection of sets is a subset of F, but an individual set belongs to F. Okay. So there is a difference you have to understand. So let this be a subset of F, be such that it satisfies two conditions. Okay. Bi intersection Bj is equal to empty for I not equal to j, and Ij equal to 1 to up to 10. And second property is union of Bi I from 1 to n is actually equal to omega. Okay, these are the two properties. These are the two properties that this collection satisfies. Then B1 up to Bn, this collection is called as disjoint cover of omega. Is the definition clear? What is disjoint cover?
Yes.
Where disjoint comes from this property and cover comes from this property. It covers omega, right? So that's why this is called as disjoint cover. Now, once you have a disjoint, sorry. Okay. So when you have a disjoint cover, then what happens? Okay. So consider this disjoint cover. So this is the definition. So we'll start with a disjoint cover. So let B1 up to Bn be a disjoint cover of omega. Okay, let this be a disjoint cover of omega. Then for any A belonging to this event set, I can write down PA is equal to PA intersection B1 plus PA intersection B2, so on and so forth, plus PA intersection Bn. Can you see this? Can you see why this will be true?
Yes, sir.
Yes, sir.
Without
It's like splitting it over the Venn diagram.
Correct, splitting the Venn. So in the Venn diagram, what is happening? In the Venn diagram, what is happening? This is your omega. This is your omega. And suppose these are the subsets. Okay, I am talking B1, B2, B3, so on and so forth, right? So these are the subsets. So this subset is B1, this subset is B2, this subset is B3, this is B4, this is B5, this is B6, this is B7, this is B8, B9, and B10. Okay, so suppose I have n is equal to 10. Okay, so B1, B2, B10, is it a disjoint cover of omega from the diagram? Right?
Yes, sir.
And now I'll consider any event A. Okay, so what is any event A? So any event A that I consider looks like this. Okay, blue circle. Then what am I doing? I am basically taking intersection of this A with respect to all the events. So intersection of A with B2 is this part, right? Intersection of A with B4 is this part. Intersection of A with B1 is empty. Intersection of A with B3 is this part, right? I am having these different parts, and this is what I am doing. I am collecting them together, right? So, okay, so I can use this color. So I hope you understand what is going to happen, right? So B5, this intersection, small intersection is here. This is B7, so that is here, and so on and so forth, right? So this is what is going to happen, right? And some intersections may be empty. So basically what I have done is A is written as A intersection B1 union A intersection B2 union so on and so forth A intersection Bn. That is how I have written my A, right? And why I can write down? So if you don't want to look at the Venn diagram, then what do you have? You have omega is equal to B1 union up to Bn, right? Then A intersection omega, which is equal to A, is A intersected with B1 union so on so forth union Bn. That will give you this set, right? Because of disjointness of B1 B2 Bn, you will arrive at this sentence that I have written down, that you either saw from Venn diagram and wrote, or from this particular set theory relation. And then now again apply axiom 3, and that will give you probability of A intersection B1 plus. So this is a very interesting observation. This is another property of axiomatic definition. So I hope this part is clear to all of you.
Yes, sir.
Have you heard of total probability law or something like that in your 12th standard?
Yes, sir.
So this statement that you have written here, PA is equal to this sum. This is actually total probability. Okay. So this particular law that we have written is total probability. We'll come to that. Okay. When I define conditional probability, which is the next topic, we'll come to that. That time I'll use this expression. So any comments, any doubt about what we have done so far? Anything that you would like to add here or say? Comments so far? Okay, then we move to the next part. So I want to define two very important concept: uniform probability space. Okay, so this is the concept. This is the concept which is very closely related to your equally likely outcome case. Okay, your intuition that you have started with. So I want to draw parallels of this with even continuum. So that's why I want to cover this. This is very important, helpful model, and we'll have probability distributions based on this uniform probability space, uniform probability principle. Okay, so this is very important concept. I want to introduce this. So the random experiment is the following. What is the random experiment? This is the experiment. Picking up a number randomly from a given set. Okay. So straightforward experiment. So I'll consider the case one. The case one is given set is finite and discrete. Okay, given set is finite and discrete. So let us consider this set 1, 2, 3 up to S. to be this set. Okay, so these are this is the sample space. And what is the experiment? The experiment is to pick a random number from this particular set. I want to pick a random number from this particular set. So probability of two subsets of omega. So what is the, so this is fine. So you know what is sigma algebra and so on and so forth. So how are we going to assign probabilities under the uniform probability space, under the uniform probability principle? So how is assignment of probabilities done? Okay, assignment of probabilities. Okay, how is this done? Assignment of probabilities. So this is the principle. Okay, so this principle is called as uniform probability principle. So what is the principle? The principle says that probability of two subsets of omega with equal size, okay, be equal. So when you are doing the assignment of the probability, please keep this in mind. Okay, what is the thing that you should keep in mind? That the probability of two subsets of omega with equal size be equal. Now here the ambiguity is in the word size. What do we mean by size? Okay, so the first question is, what do we mean by size? So in case one, where you have omega to be equal to the finite set, collection of numbers 1, 2, 3 up to s, what do you think is size of a set? What can you define as size?
The number of elements in the set.
Correct. Number of elements in the set can be a good way to measure the size of the set. Okay, so you see I'm using the word measure. So that word measure is actually used in the definition of probability also. I said probability measure, right? And then I said if you don't want to use the word measure, just forget it. But that is the origin of the measure theory that I'm saying, right? Measure theory, advanced set theory and all. So that origin of the word measure comes from here. What is the way in which we will measure the size of a set? That is what is measure. Okay, so here we say the cardinality of the subset. Okay, so in case one, so let us write down here, in case one, when omega is finite and discrete. Okay, discrete and finite meaning that it is of this particular form. Okay, it is finite and discrete, that means it is of this form. Omega is equal to 1. We can associate size to the cardinality. Okay, we can associate size to cardinality. So certain set is bigger in size than the other set will mean that that particular set has more number of elements sitting inside. Okay, so as a consequence, of this, we can see very easily that all the singletons are of same size, right? What is the size here for all the singletons? Same size. Size is actually 1. And hence, what should be the probability according to the uniform probability principle? Can you tell?
1 by s for every.
Correct. According to the uniform probability principle, what should happen? Probability of every singleton k is equal to 1 by s for k is equal to 1 to up to s. Correct? So that is what is happening. So this space, so this probability assignment, and we have already seen that once you assign probability to all singletons, then your total probability assignment is done, your job is done, right? That's sigma algebra and so on and so forth. So probability of k is equal to 1 by, so this particular space, this particular probability space, so this probability space, so what is the probability space? I'll just write down. The probability space is omega f and this probability assignment. Okay, so this triple together is called as probability space. This probability space is called as discrete uniform probability space. So what are the examples of discrete uniform probability space? If you toss a fair coin, then heads is half, tails is half. If you roll a fair die, then 1, 2, 3, 4, 5, 6 all have probability 1 by 6. If you have a deck of cards and each card can be picked with equal probability, that is 1 by 52, then that's uniform probability space, right? So these all fair examples, so to speak, that you have learned in so far in your 12th standard, they all belong to this particular class of discrete uniform probabilities. Okay, so that is what you had mainly learned. Equally likely scenario having probabilities like that, it was discrete uniform probability space. So is this idea of discrete uniform probability space clear? Then we go to the next idea. This is straightforward, right? The only key thing is how do you associate size of the set? You say the size is associated with cardinality, and then your job is done, right? Now let us consider the other case. Okay, so I will consider other case. The case is of case 2. The given set. So remember, what was the experiment? The experiment was picking up a random number from the given set, and the case was a random number is to be selected randomly. A number is to be selected randomly from finite discrete set where omega is equal to 1, 2, 3, 4 up to s, right? So now I'll say the case 2, the given set omega from which you are choosing the random number is finite. So you see I am using these words is finite and an interval of r. Okay, so for example I will take this. Okay, in particular consider omega to be equal to 0 to 1.
How can we call this set finite?
Yeah, so what do you mean by finite? That's the question we are asking. That's why I underlined finite. So if you mean by finite set, the set which has only finitely many elements, then this set is obviously not finite. It contains infinitely many elements. In fact, it has more elements than the set of natural numbers also, because this is an uncountable set. So in that way, this set is definitely infinite, but I am still using the word finite because I am using it in another context. Okay, so that context will become clear. So I am using it in the context of size of the set. Okay, so once again, principle of uniformity. What does the principle of uniformity say? Pick two subsets of omega. Pick two subsets of omega. What is omega here? Omega is closed interval 0. Pick these two subsets of omega of equal size. Okay, so again, this size is very important. Then they should have, then they shall have same probability. Correct? So now how do you define size? What is the size of? Here you can take length as the size, right? So here the length can be treated as size of the set, right? So this intuition again is very important. I am happy that you have that. So let AB be a subset of 0, 1. Interval AB be a subset of 0, 1. Then size of AB can be associated with the length of this interval. Given by B minus A. So with respect to this understanding of size of the set, can I say the set 0, 1 is finite?
Yes.
Huh? That's the context in which I am using the word finite here. Okay. So the length of the interval is B minus A, and in that context, I'm saying the set is finite. The size of the set is finite. Okay. So now I have to do probability. Excuse me. I have to do the probability assignment. So how will I do the probability assignment now? Any thoughts?
Based on the length, we can do like B minus A divided by 1.
Correct. So probability assignment. How will I do probability assignment? I'll do probability assignment. Take any interval of form AB, right? Any interval of the form. What is probability of AB? It's the length B minus A for any AB which is subset of 0, 1. Is that right? So I'll be a little more careful and I will use the same one that I had used in sigma algebra. So what is the sigma algebra that I'm considering? Sigma algebra obviously that I'm considering here is Borel sigma algebra, right? Sorry, sigma algebra is Borel sigma algebra. So every set in the Borel sigma algebra will have the probability. And what will be the probability of any interval? The probability of any interval will be the length of the interval, B minus A. Do you understand this? Is this part clear so far? So what this probability of interval AB really means? The probability of interval AB really means that the probability that a random number is selected between A and B is B minus A. Is that okay?
Yes, sir.
You're following this, right? This is something that is really very, yeah. So this particular space.
Sir, why are we taking here B closed? Is there any particular reason?
I am taking B closed because I think in that example also I took B closed. In this example, here also I took B closed, na? A open, B closed. There is no particular reason why I am taking A open and B closed. Okay, I could have taken A closed and B open, or I could have taken A, B both open, or it doesn't matter. Okay, any combination I take, I will still get the same Borel sigma algebra. That's not a problem. So that's why I became little careless here initially when I wrote down A and B both open. But then I remembered that in the example that we discussed in the class, I took A open and B closed. So I changed it like this. It doesn't really matter because length of all these intervals is still B minus. Okay?
Sir,
Yes.
sir, if we take A and B both open, then I think we'll not get singleton 0.
Why? You will have complement. With the complement, you will have the closed interval. Then you can form a sequence of sets which will converge to singleton 0. You can have.
Sir, if we are taking open interval from 0 to 1 and then complement of that, so it will have both 0 and 1.
See, that is not an issue. You can generate all singletons. Why? Because you have 0 to 1. If you take any open interval, then you can take the open interval. What is the open interval? I'll take half 1. Okay, that is the open interval I take. What is the complement of half 1?
0 to 1 by 2
and singleton 1. Okay.
Yes.
So I will continue doing this. Okay, so half 1, and then I will construct the sequences, right? So then what will happen? Okay, there is some simple algebra that you have to do. Okay, let me figure out, but you can do it. Okay, so if you are not comfortable with both open, you take one open, one close. That's also fine. You will get the Borel sigma algebra. Okay, so for the time being, you consider one open, one close, but it is not really necessary. I'll construct the example and I'll show. Right now, it's not coming to me, but it's possible. Okay, so I'll remember your doubt, Dhruv. I'll try to give you an example. Okay.
Yes, sir.
Yeah.
Okay.
So can you give a different example regarding this property?
Which property?
This property you are explaining, can you give a different example regarding this?
Which example? Like what property?
Just we are discussing probability assignment regarding this length, this continuum.
So this is one example that I am taking. There will be many such examples of probability assignment we will learn throughout this course. I'm just taking one of the simplest examples. Is that okay? Okay. You will see many such examples of the continuum later on. But right now we are doing principle, like we are doing probability assignment with uniformity principle. Okay. Later on, we'll not do assignment with uniform probability principle. Then you will get different probability spaces. Okay, we'll do that also. Many examples will do. So this is Borel sigma algebra, and this is continuous uniform space. Okay, so this space, this is the continuous uniform probability space. What is probability of this set? Huh?
0.
0.
So probability of all singleton sets is 0. Is it not? So probability, in fact, is this true or false?
True.
True.
Does this bother you?
Tends to 0.
No, what tends to 0? What tends to 0? Can you please tell?
P of
Probability of singleton set.
It tends to 0. It is not 0.
So we can't write it in a limiting form if it's not tending to 0. If we assume it's 0, then we're trying to integrate it
right?
all over the set. So it's
Then
tending to 0. It's very small.
Why?
That we don't care about it.
No, it is absolute 0. If it is small and we don't care about it, in probability we still will care, because probabilities are very small in general. So we will care about small probabilities also. But here it is absolute 0, na? Like singleton.
Excuse me,
set.
sir.
Yeah.
Yeah, the way in which we defined the size in case 2, using that definition, the length of a single element is 0.
Okay.
Therefore, this will be exactly 0 for any single element.
Correct. So in
Okay.
fact, it is 0 for every singleton set, single element between 0 to 1. But I'm asking, is that bothering you or not?
No, sir,
Yes, sir.
because it.
Yes, sir.
Why?
Because
Sir, yes, sir.
it's 0, but it's still possible.
No, so why is it bothering you?
So because even though the probability is 0, it is still possible.
What
We
is
can
possible?
get that number. For instance, we could get, if we randomly choose between 1 and 0, we will get a number whose
Yeah.
probability would be 0.
So what is happening here?
So that is the difference between probability in continuous and discrete systems.
Okay, but is that the only point of botheration?
Sir,
Uh-huh.
so
Bolo.
all these, so the union of all these singleton sets will give us the complete set, but the sum of all these probabilities will not give us one.
ये तो contradiction आ गया. YouTube वीडियो डालना पड़ेगा. 1 is equal to 0. हाँ, ये क्या हो गया?
That's why I told it tends to 0, sir.
अब क्या करेंगे? How will we resolve this?
Sir, the problem is with the definition of size, I think.
So far you were happy with the definition of size.
Sir, it's
Sum
safe
of
to say it works when the size is sufficiently comparable to 0 to 1. If it's like a singleton set or 2 elements, then you can't do anything right.
No. If you have to have a theory, it should be uniformly applicable everywhere, right? You cannot say इसके लिए कर सकते हो, उसके लिए नहीं कर सकते. ये तो ऐसे हो गया, सुबह 8 बजे सब लोग उठ के नींद से बैठे 2 घंटा कुछ तो किया, एक्सियम सेट किया, and finally we are proving 1 is equal to 0 at the end of the class. Okay, so now you have to be really very careful. Okay, and this is the place where you will really start appreciating the beauty of mathematics. Okay, this is something that is really very important. So first things first. Okay, so everybody agrees that this A belonging to 0 to 1 is equal to interval 0 to 1. Everybody agrees with this statement. There is no doubt about it. You take you take union of all the singleton zeros, you are getting this. Now one thing that you have to understand, why that sigma is coming. I could not say why algebra is coming, but I will tell why sigma is coming. What is the role of sigma? Sigma means summation, right? Many times we use summation symbol. Where does summation occur? You see the definition, we were explicit. We said that this axiom 3 holds only for countable union. Only for countable union. I from 1 to infinity. The union that we are taking here, is it countable union?
No, sir.
Is this union countable?
No, sir.
So if this union is not countable, then can we apply axiom 3? Can we apply axiom 3 here?
No, sir. No, sir.
No, so 0 is equal to 1, ये तो केस रूल आउट कर दिया हमने, क्योंकि हम वो नहीं लगा सकते. The union on the left hand side that you are seeing is not countable union. It's in fact uncountable union. So you see the power of countability and uncountability here. The true essence of infinity is starting to get reflected here. Okay, every singleton point here has probability 0, but the length of the interval is still 0, 1. That is 1, length 1. So what you are essentially saying here, is that the singleton point has length 0. So with the logic, because you are taking union of all such singleton points, the length of the interval 0, 1 also should be 0. Because I am only talking of length. No, probability is just name given to the length in this particular instance. But that's what you are essentially talking about. Do you see the point? So the uncountable union has this some weird magic in itself. Countable union does not have this magic. But uncountable union somehow has this magic in itself that you take uncountable union of length 0 sets, you get length 1 set. Are you able to appreciate what is happening here? Okay, we are not going to do anything more than this today. This is one of the most important and profound concepts about infinity that you need to learn. Okay. Are you all with me? Are you understanding the true difference between countable union and uncountable union?
Yes, sir.
And now with this in mind, with this context in mind, are you able to appreciate how small the set of natural numbers is even in front of this closed interval 0, 1?
Yes, sir.
Yeah, it's such a small set, small in the sense the number of elements small. Okay, so the infinity that you are looking at within 0 to 1, even if it has finite length, the infinity that we are looking here in 0, 1 is like much bigger than the infinity of set of natural numbers. Is that okay? Is that appreciable? So there is no contradiction here. Okay, there is no contradiction here. We are not having 0 is equal to 1 case, because this union has to be a countable union. It is not a countable union. Because it is not a countable union, you cannot apply axiom 3 of probability. Because you cannot apply axiom 3 of probability, there is no problem. You are not saying 0 is equal to 1. But length of singleton set is 0. So the probability of singleton element is still 0. But it does not harm us, right? It does not harm us. So this singleton 0 is an element of F. All the singleton sets are elements of F. All the intervals are of the elements of F. All the singleton unions and their countable union, intersection, everything, all those type of sets are in F. And all these sets will be assigned the proper probability. So for example, what is the probability of this set in uniform probability principle? What is the probability of this set? This probability is also 0 because this set can be written as countable union. Do you agree? This particular set, I can write down as countable union of singleton sets of the type 1 by 2 raised to I going from 0 to infinity, right? So this is a countable union, I going from 0 to infinity. I is taking value 1, 2, 3, 4, 5, 6. I can count it, though it is infinity, I can count it. In this union, when A was taking values between 0 to 1, I could not count. There are more elements than I can count, right? So that's the difference, uncountable versus countable. So probability of this set is 0. What is probability of 1 by n belonging to a natural number? This set, this probability is also 0.
Yes, sir.
Because
Yes, sir.
this set is also a countable set. So you pick any countable set which is a subset of 0, 1, the probability of that set is 0. Do you understand what is happening here in this uniform continuous probability space? Okay, these are the things that you have to appreciate. Okay, these are the things that you have to understand, and this is where the true nature of probability comes into the picture. Okay, वो सब equally likely events हमने बहुत किया 12th standard में. अब इसमें देखना है what is really happening. Okay, we have to understand probability from this context. So what am I able to? Yes. Go on. Yes.
So by the way, from this, we can say that, right? That we cannot tell that the disjoint cover of an uncountable set is a set of countable sets. Means that will also be uncountable sets only. We cannot make an uncountable set only from countable sets.
You cannot make an uncountable set from only countable sets. That's right. You cannot do that. Because countable union of countable sets is also countable. You are absolutely right. It's a very good observation. You cannot make uncountable set from countable unions. Never. So have you seen, this reminds me, have you seen those very nice videos that are available in YouTube? I will try to find and share the link with you. It explains about all those problems, no? Some hotel, Hilbert's hotel problem, a room with infinitely many guests. Like,
Yes,
sorry,
sir.
a hotel with infinitely many rooms, numbered 1, 2, 3, 4. Then one guest arrives, what happens? You shift everyone to the next room and then you accommodate. So anybody who comes to the hotel will always get a room. The guests have to shift the room. Now a bus full of countably infinite people come and they want to be accommodated. Then you send every person to the room number, which is 2x, right? So 1 goes to 2, 2 goes to 4, 3 goes to 6. So all the even numbers are filled and odd numbers are remaining. So you fill those countably infinite people into odd number of rooms, and so on and so forth. So what you are saying through this analogy, you can see how the countable union of countable sets is still countable. Okay. So this infinity business now, it's really very fascinating. You should be, always looking up at all these things. So you have set of natural numbers. You are saying number of elements in set of natural numbers, counting you are doing. So is the set of odd natural numbers have less number of elements than set of natural numbers? You are tempted to say half, right? You are tempted to say half. Odd numbers are only half of the total.
Since they are the subset of natural numbers, so they. I mean, we can't say less or more in infinity in a direct way. So I'm not.
No, they have exactly
Yeah.
same number of elements. For every number I, you have a 2i. For every 2i, you have a I. So there is a 1-to-1 correspondence between these two sets, no?
Yes, sir.
And still it is a proper subset of that set. Set of even numbers is a proper subset of set of natural numbers, right? This is not possible in a finite set, right? In a finite set, if a set is subset proper, then the number of elements have to be strictly less. But in case of infinite set, that does not happen. You see, the beauty of infinity starts from here. So, this is something that you have to appreciate. And still, the probability of choosing a odd number from the set of natural numbers, that probability is half. So that half that you had in your mind is somewhere there doing something. It is not going anywhere. That intuition of half is reflected in probability, though not in the set of number of elements. Okay. So all these things are really beautifully interconnected and these things are really beautifully intertwined. Okay. So it's just that we have to kind of wake up, start looking at them, stare at them, think about them, and start appreciating beauty in them. Okay, so this is about uniform probability space. We'll get into more details of this probability spaces. We'll have various examples, not only of uniform probability spaces, but much more when we start learning spatial probability distributions. Okay, but this is what I wanted to cover. This is the kind of idea starting point. Okay, this is the definition of probability. So these are advanced things, though we will not dwell too much into these type of things. We will now move on to the next topics like conditional probability and all from the next class. But these are the things that I will say you really need to appreciate and you really need to look at. Okay, not from the exam point of view. Okay, exam point of view से पढ़ोगे तो कुछ नहीं होगा. But for the sake of understanding, these things are really beautiful, and I would really love to talk to you about these things in detail some other time. But as far as course is concerned, we will stop at uniform probability spaces and these things, this sigma algebra and all these issues, all these things. But this point will come recurrently. Okay, probability of singleton is 0 will come recurrently in any continuous probability space. So you need to understand this properly anyway. So think about all these things and we will meet next week once again. We will stop today. Any doubts about what we have done? Any comments that you want to have on this?